Our fifth lecture video on fluids will discuss buoyancy. In order to discuss buoyancy, we will first talk about Archimedes' principle. Archimedes' principle tells us that the upward buoyant force exerted on an object in a fluid, whether it is fully or partially submerged, is equal to the weight of the displaced fluid. In this picture, we can see an empty ship. An empty ship rides higher in the water because it doesn't weigh as much, so it won't displace as much fluid. However, a fully loaded ship displaces more water than an empty ship and rides lower due to the increased weight. The buoyant force is the upward force exerted on a submerged or partially submerged object. An equation that we can use to solve buoyancy problems is that the object's weight in water is equal to its weight in air minus the buoyant force. The buoyant force is essentially the weight of the displaced water. In this picture, we see some arrows pointing up. These upward pointing arrows represent the buoyant force acting on the swimmer. Let's take a look at a couple of examples relating to buoyant force. A chunk of steel weighs 88.0 newtons in air and 76.0 newtons in water. Find the buoyant force of the water. First, let's write down the data we were given. We know the weight in air is 88.0 newtons. The weight in water is 76.0 newtons, and we are trying to find the buoyant force. The basic equation is that the weight in water is equal to the weight in air minus the buoyant force. Since we are trying to find the buoyant force, we need to rearrange to get that the buoyant force is equal to the weight in air minus the weight in water. Next, we can substitute the data we were given. The buoyant force is equal to 88.0 newtons minus 76.0 newtons. This gives us a buoyant force of 12.0 newtons. Let's look at one more example. A flat-bottom fishing boat is 5.00 feet wide, 14.0 feet long, and 3.00 feet deep. How many cubic feet of water will it displace if the top stays 1.50 feet above the water? First, we will write down what we know. We are given the dimensions of the boat. It has a length of 14.0 feet, a width of 5.00 feet, and the height is 3.00 feet, but we want the top to be 1.50 feet above the water, so we will take 3.00 feet and subtract 1.50 feet to get a depth submerged of 1.50 feet. In order to figure out how much water it will displace, we basically need to find the volume of the boat. The basic equation to find volume is that volume is equal to the length times the width times the height. Last, we can substitute in our data. So the volume is equal to 14.0 feet times 5.00 feet times 1.50 feet. This gives us a volume of water displaced of 105 cubic feet. The second part of this question is what load in pounds will the boat contain under these conditions if the empty boat weighs 175 pounds in dry dock? We need to find the buoyant force, which is the same thing as the weight of the displaced water. To find this, we will take the weight density of water and multiply it by the volume of water displaced. The load force that the boat can hold will be the difference between the buoyant force and the weight of the boat in dry dock, or essentially the weight of the displaced water minus the weight of the boat. Now that we know what we are going to do, let's write down the information we are given. We know the volume from the previous part is 105 cubic feet. We also know from a table that the weight density of water is 62.4 pounds per cubic foot. We need to find the weight force F sub W. The basic equation to find the weight force is that the weight density of water times the volume of water displaced will give us the weight force F sub W. Next, we can substitute. 62.4 pounds per cubic foot times 105 cubic feet will give us a weight force of 6,550 pounds. However, like I already mentioned, we need to find the difference between this weight force and the weight of the boat in dry dock to figure out how large of a load the boat can hold. So we will take 6,550 pounds and subtract 175 pounds to get 6,375 pounds, or, using correct significant digits, 6,380 pounds. This concludes our discussion on buoyancy.